the IHT function is talk about k, which is the sparsity level we want to enforce in the wavelet domain. And this is essentially just the number of non-zero elements to save from psi. Um, and this k-frac is that as a ratio. So we're going to say 5% of the coefficients in the wavelet image. Now, for the IHT function, we want to give it the destroyed image, the sparsity level, the wavelet function and its adjoint, the linear destruction operator and its adjoint, the number of iterations we want to perform IHT on, and X init. So this is our initial guess of the image, and this can be really productive to make the algorithm a lot better, because often there's some really easy work we can do before the algorithm to make the algorithm better and get a better final solution. So in the deblur case, I didn't do anything, but if we look at the in-painting example, we can just fill in all those holes with the nearest neighbor interpolation, and same thing with the demosaicing. And the reason we want to do stuff like that is that IHT is not a convex algorithm, meaning if you just let it keep running no matter what, it's not going to find the optimal solution. So we often want to try to get as close to the optimal solution as possible so that it'll converge on something hopefully pretty good. And then xtrue is just the original image, and this is not part of the algorithm. This is just something that we can use to evaluate the algorithm over time. And same thing with return movie. This is just whether you want to return a sequence of images of the progress of the estimations while IHT has been training. T function, this is what we want to solve for, this loss function here. We want to minimize S, we want to minimize this loss function for S, and S is the wavelet transform of the image we're trying to predict. The first part of this loss function is really just the normal L2 norm pseudo-inverse solution. And that's not very interesting. What's interesting is that we've stitched on this constraint, this sparsity prior, where we want the L0 norm of S to be at most K. So there can only be at most K non-zero elements in our predictions wavelet transform. An iterative process that's going to start out with just normal gradient descent. We get an eta, or learning rate, scheduled that's going to start out as a large number, maybe 0.5, and get smaller and smaller and smaller over time. And so this is going to be how much we jump in our gradient descent each iteration to improve the image. And so next we calculate the gradient. This is just the normal L2 norm portion of our loss functions gradient. And then we update the image with that gradient. So this next part, we do the sparsity prior enforcement. So we first take the wavelet transform of our estimate, then we partition all of the values of this S image, of this wavelet image, instead of sorting it. So we could sort it and then zero out the smallest ones, but a partition is going to do the same thing, but it's going to be a lot faster. Instead of which sorting is n log n time, this partition will be O of n time. So we're going to get all those indices, zero them out in our wavelet transform, then undo the wavelet transform to get our new estimate. And this zeroing out process of these low energy elements is essentially ideally going to get rid of a lot of the noise and bad features in our estimate. So that we just keep repeating this process over and over again for max iterations. We could also add a convergence portion to this where we decide, it automatically decides when it's converged or not. I didn't do that, but it would be, you could add that if you wanted to. Down here is this, just evaluating the progress of our algorithm. This is obviously under the assumption that we know the true solution, but it's just for tracking purposes. And here we can, if we want, we can save a movie of each of the frames during the iterative estimations. So over here, The IHT function is going to be just a little bit different for a color image or for the demosaicing problem. Here, um, everything's the same, but we have three color channels that we need to apply this wavelet transform on, um, and we don't want to just zero out them individually. Uh, and the reason for this is that these gradients, the smoothness of the image goes across all three channels. So we want to combine them, and we can either combine them with the mean or the norm, or there's probably a bunch of other ways you could combine these. That'll work pretty well. Taking the max between across the same indices down each channel. Um, but anyways, we want to combine them into one image, and then we want to take the partition and those indices that we choose will apply, that we want to zero out, will apply to all three channels. Rather than them doing individually, they get zeroed out in the same location everywhere. And this will create a better result. And then again, we take the mean squared error and save the movie. This algorithm, I just wanted to show you that all the helper functions were here. Um, the adjoints of these functions of the linear operators is pretty easy to solve for in this case. The blur is just inverting the axes, and for the mosaic and corruption, it's the same. The adjoint and the um, linear operator are both the same. Another important function, I think it would be nice to highlight, is this fill holes function, where we use SciPy's interpolation package to do a 2D interpolation with the nearest neighbor method to fill in those holes. So let's go over and look at the results. The first one I want to highlight is the demosaicing results. Right here we have the original image, and this is what the mosaic looks like without any work done. And if we just take this image, image with lots and lots of holes in it, and put it into IHT, we get something like this. So it smoothed out a lot of things like the cup, the wall, but it kind of still, this is a pretty crappy job. You could almost say that this image looks nicer. There's a lot more blur here. But if we just fill in the holes, we get a pretty damn good image right here. So this is, IHT didn't do any of this work. But you do notice that the edges are kind of weird, right? There's these like rainbows, these color inconsistencies along the edges. Because nearest neighbor doesn't know anything about edge. It could be copying like this it could copy this pixel from anywhere along the edges. So IHT, and the reason it does great here is because the nearby pixels are really good. If there's a whole blob of white, copying over a white pixel is great. But when you have different colors and steep slopes, a lot of mistakes will be made. So here we put that image through IHT, and it sharpened out the edges. Now we don't have these weird rainbow patterns along the edges, and it looks much nicer. Next we have the de-blurring image. So this we didn't do any pre-processing for. We just took the blurry image, put it into IHT, and we get a much sharper image. Really nice. Finally, we have the in-painting. So this the original image, the corrupted image, and this is what it looks like when we fill it with holes. You can still see there's not rainbows, but you can see the edges are disjoint because the nearest neighbor copying could have made a lot of mistakes along the way. And then see all those little edge inconsistencies get cleaned up in the IHT image. Though it did seem to create some problems with like dimming the image some. So it's not perfect. There's probably things you could do to refine it a little bit more and make a better image than this. But this is the general premise of the algorithm. I hope you learned a lot about, or at least a little bit about, image processing and this idea of a sparsity prior, where we want to leverage the natural features of an image. Thanks for listening. Let me know in the comments if you want any more explanations of why things are happening, or if you just want to talk about anything. Thanks.